So let's do a different population modeling. This is called a predator-prey model. So suppose we want to model populations of foxes and rabbit after K month. Okay, so the FK be the fox population in month K, and RK be the rabbit population in month K. Alright, so we have a slightly different relation compared to the previous one we saw. So in this one we have f of k plus 1. A month later, the fox population is equal to 0.4 times fk plus 0.3 times rk. And rk plus 1 is negative 0.4 fk plus 1.2 rk. So let's interpret this a little differently. So this term means only 40% of foxes every month. Only 40% of foxes survive without rabbit. If there's no rabbit, then only 40% will survive. But if there's rabbit, then this term is the population growth, fox population growth, supported by the presence of rabbits. So the more rabbit is, the faster the fox grows. All right, so those are the first equation, and then in the second equation, this term represents, this is every month, the population grows, the rabbit population, by 20% without the presence of fox. So that means if there's no foxes at all, then every month the rabbit population grows by 20%. But some of them get eaten by foxes. So this is the rabbit population eaten by foxes. So the more foxes there are, the more rabbits they're eaten. So there is some sort of weird balance here. So we want to see what happens. We want to see what happens after a long time. So let's do this. So we can also write this in terms of matrices. So f of k plus 1, rk plus 1, a vector, this is equal to 0.4 fk plus 0.3 rk, negative 0.4 fk plus 1.2 rk. This is equal to the matrix 0.4, 0.3, negative 0.4, 1.2 times fk rk. So let's, if we call this A, then the fox and rabbit population after k months is equal to a to the k times the initial fox and rabbit population. So again, it reduces to computing a to the k. All right, so we're not gonna calculate this whole thing again. So you can refer to the textbook, but A can be diagonalized into PDP inverse. So the eigenvalues are 1 and 0.6, and eigenvectors are 1, 2, and 3, 2. And we have a formula for inverse, so if P is that P inverse is 1 over the determinant, which is negative 4, times 2, negative 3, negative 2, 1. Okay. So same thing, we want to see if the fox and rabbit populations achieve an equilibrium. So we want to see what happens as k goes to infinity. So a to the k is e p times t to the k times p inverse, which is 1, 3, 2, 2 times d to the k. This is just a diagonal entries taking the k power. So 1 to the k, 0, 0, 0.6 to the k times negative 1 over negative 4 times 2, negative 3, negative 2, 1. Okay, so as k goes to infinity, 1 to the k is just equal to 1, but 0.6, because it's less than 1, so this goes to 0. So a to the kth is equal to 1322. Again, 1000 times negative 1/4 times 2, negative 3, negative 2, 1. Okay, this is equal to negative 1/2, 3/4, negative 1, 3/2, using calculators. Okay, so suppose the initial population, let's again assume there are 50 foxes, 50 rabbits initially, then fk after k months, as k goes to infinity, is equal to a to the k times 50/50, which is equal to this matrix times 50/50, and this is equal to, let's see, 75, this is 25, so and the first term is, let's see, minus 25 plus 37.5, so this is 12.5. Okay. So as k goes to infinity, eventually the fox and rabbit populations reach an equilibrium. So this is the limit as k goes to infinity. So eventually the fox and rabbit population stabilizes. Okay, so let's change a little bit. So let's suppose fk plus 1, rk plus 1 is 0.4, 0.3, negative 0.5, 1.2. So this term on the bottom left originally was negative 0.4, now it's changed to negative 0.5. So this means the foxes are hunting more rabbits, so that the rabbits population decreases faster if there are more foxes. So we change it to negative 0.5. All right, so let's see what happens. So this is still a matrix A. Again, we're not going to calculate the whole thing again. A can be diagonalized. This time the eigenvalues are 0.9 and 0.7, and the eigenvectors are 3, 5, 1, 1. Okay, so A is diagonalized, so a to the k is p times d to the k times p inverse. So same thing, we want to see what happens as k goes to infinity. So a to the k is p times d to the k. D to the k is just the diagonal entries to the kth power. And then p inverse. As k goes to infinity, you notice that both eigenvalues are less than 1, so both of them goes to 0. So as k goes to infinity, d to the k power is just a 0 matrix, which means a to the k is p times d to the k times p inverse, but the middle one is a 0 matrix, so this is just a 0 matrix, which means 0, 0, 0, 0. So that means as k goes to infinity, fk fox population and rabbit population equal to a to the k times the initial population. But it doesn't really matter what initial populations are because this is 0, so this is just equal to 0. More precisely, 0, 0. So technically, it also reaches an equilibrium as in eventually both foxes and rabbits go extinct. Okay, So let's do a third case. So let's suppose fk plus 1, rk plus 1 is, let's see, the three entries, positive entries are the same, but the bottom left entry is smaller. So this entry is a little smaller. This means the foxes are hunting less rabbits. So basically, you can think that the foxes are trying to be more sustainable. More sustainable. Okay. All right. So this is the matrix A. Let's quickly calculate the eigenvalues and eigenvectors. A is PDP inverse. The eigenvalues are 1.05 and 0.55. The eigenvectors are 6, 13, 2, 1. You can calculate the inverse quickly. So the inverse is 1 over the determinant, which is negative 20. Swap the entries around, 1, negative 2, negative 13, 6. Okay, so a to the k is p times d to the k times p inverse, which is 6, 2, 13, 1 times d to the k is the diagonal entry to the kth power times p inverse. Okay, so as k goes to infinity, this goes to 0. So we don't want to put infinity on top left. We want to see how fast the terms grow. So let's keep this term. So as k grows big, a to the k is roughly these three matrices multiplied together. So it's 6, 2, 13, 1 times 1.05 to the k, 0, 0, 0 times negative 1 over 20 times 1, negative 2, negative 13, 6. And if we use calculators, multiply all these together, this is equal to negative 120 times 1.05 to the k times the matrix 6, negative 12, 13, negative 26. So suppose initially there are 50 and 50 foxes and rabbits, then after k month is roughly equal to a to the kth times f0 r0, which is equal to all these multiplied together. (50-50). So this is equal to, oh great, that's 300 minus 600, negative 300 divided by 20. 300 divided by 20 is 15, and that's 650, 650, 650, negative 650, yeah, negative 650 divided by 20, negative 65, 65 divided by 2, which is 32.5. Okay, I think that's correct. So basically, in this case, there's no equilibrium, so this is not technically not equilibrium. So eventually, both foxes and rabbits grows at the rate of So this term tells you it's about 5% a year, a month. So this is probably the best scenario among the three because we made the fox more sustainable. So eventually the fox and rabbits are growing steadily at a constant rate. All right.